Yogah Karmasu Kaushalam.
I am Nikita Mishra from Department of Chemistry, Gujarat University. Welcome you all in the online refresher course in chemistry on behalf of Dr. Jagdish Joshi, Professor Director, UGC HRDC, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, Department of Chemistry, Gujarat University. The next session is Dr. Vinay Kumar Singh, Associate Professor, Department of Chemistry, Faculty of Sciences, MS University, Baroda. Dr. Vinay Kumar Singh received his MSc in Chemistry from the University of Gorakhpur in 1996. He completed his PhD from Banaras Hindu University, Varanasi in 2001 in the area of synthetic coordination chemistry. From 2001 to 2005, he was postdoctoral fellow at Indian Institute of Technology, Bombay. In 2005, he was appointed as an assistant professor in chemistry at the Maharaja Sayajirao University of Baroda. He received an award of Young Scientist by the Ministry of Education and Science of Spain to pursue postdoctoral study at the University of Cadiz, Spain during May 2007 to October 2008. Since December 2017, he has been working as an associate professor at MS University of Baroda. He is currently exploring the coordination chemistry of 1,1-dithioligands such as dithiocarbamates and xanthates through coordination-driven self-assemblies of ferrocene functionalized amine alcohol proligands with carbon disulfide and transition metal ions as well as organic building blocks targeted towards anti-tumor and antimicrobial activities. Simultaneously, he is also working on NO-SCIF-based complexes as well as mononuclear transition metal acetinides complexes that are well known for their high catalytic activity in various organic and organometallic transformations. He is an author of over 35 publications and 3 students have been awarded PhD under his supervision. He has guided 15 MSc dissertation students and 6 PhD students are currently working under his supervision.
Hi everyone, myself Dr. Vinay Kumar Singh from MS University of Baroda. I thank UGC HRDC of Gujarat University for giving me an opportunity to connect with you and to deliver my session on frontiers in organometallic chemistry. I would like to thank Professor Jagdish Joshi, Director of UGC HRDC, and Dr. Dilip Vasawa, Course Coordinator, Department of Chemistry, Gujarat University, for organizing such a wonderful program. As I know, HRDC Gujarat University is ranked as 15th in India and number 1 in Gujarat. I am very glad that it is one of a very few HRDCs which have very successfully organized many programs such as orientation, refresher, and short-term courses. Recently, in the year 2019-20, a record break program with 9,000 participants on online annual refresher program in English language teaching has been completed with grand success. Professor Jagdish Joshi and his team have accomplished many such programs in recent past. I am glad to be a part of this program and feel happy to deliver my talk on frontiers in organometallic chemistry. So this is going to be the content of my talk. I have divided my talk into 2 parts. In part 1, I'll be talking about the historical development of organometallic chemistry, main group, and transition metal organometallic compounds with selected applications, recommended books. In part 2 of my presentation, I would like to cover recent developments in the area of bioorganometallic chemistry, where I'll be able to share some of our recent research achievements in the area of organometallic chemistry. So to draw the attention of young participants who are from different backgrounds, and just to let them refresh about the importance of organometallic chemistry, I have kept this slide. As you can see that so far 5 Nobel Prizes has gone to the researchers who have contributed in the area of organometallic chemistry for their discovery of Grignard reagent, Ziegler-Natta catalyst, sandwich compounds, hydrogenation and oxidation catalyst. Grubbs and Schrock have reported a very versatile ruthenium carbene catalyst in the year 2005, which is used in the ring closing metathetical reactions. Now going through the historical development of organometallic compounds, tetramethyl diarsine, commonly known as cacodyl, is supposed to be the first main group metal alkyl complex discovered by a French chemist L.C. Cadet during the year 1760. Soon after the discovery of this main group alkyl compound, a whole series of metal alkyls of this type for a range of metal atoms starting from lithium to tellurium have been reported in the literature. This G salt is supposed to be the first platinum olefin complex reported in 1827. Friedel and Krebs have reported organoserine compounds during the year 1863. Discovery of nickel tetracarbonyl Grignard reagent have been made during 1819 and 1899. Like many other organometallic compounds, Grignard reagent and nickel tetracarbonyl, they are very versatile synthetic reagents used in the organic as well as organometallic transformations. First sigma alkyl complex, diene complex, first hydride complex were reported during these years by different investigators. Discovery of ferrocene have been made during 1951. Ziegler-Natta catalyst involving trialkyl aluminum compounds were discovered during 1955. Vasquez complex, which is a very versatile homogeneous catalyst, was discovered during 1962. Fisher has reported tungsten carbene and tungsten carbine complexes during the year 1964 and 1973. A first example of olefin metathesis were surfaced during 1964, which involves the rearrangement of alkyl groups between two olefinic compounds, as you can see it here, exchange of R groups between two olefins. Schrock have reported tantalum carbene, tantalum methylene, and tantalum carbine compounds during 1974. That nature has synthesized an interesting organometallic compound, cobalamines, which contains cobalt carbon bonds in the molecular structure. As you know that organometallic compounds must contain at least one metal carbon direct linkage. So coming to the classification of organometallic compounds, the classification of such compounds can be made on the basis of nature of hydrocarbyl ligands as well as on the basis of nature of metal carbon bonds. So here, this is one type of classification. As you can see here, that compounds are classified as monohepto, dihepto, trihepto. It all depends upon the number of carbon atoms of hydrocarbyl ligands interacting with the metal center. Say for example, in this case, in the case of metal alkyls, metal vinyls, metal carbene, metal carbine, as well as metal halides, only one carbon atom is interacting with the metal. So all these compounds are known as monohaptotype. In the literature, there are compounds, octahepto compounds known with octaheptoligands. So actually, these monohepto compounds, which includes metal alkyls, metal vinyl, metal carbene, metal carbene, metal halide, they don't come under the same series. Basically, they forms a different class of organometallic compounds. They have their own background, they have their own applications, reactivity pattern. So although they are classified as monoheptotype of compounds, but they forms a very different class of compounds. I'm going to talk in detail about one type of monohepto compound, that is metal halides, in some detail. As you can see here, transition metal halide compounds are considered as a versatile ligand used in various organic as well as organometallic transformation reactions. And apart from that, they are useful in the area of material science. As you can see it here, there is a review article published in Engine Academy, which describes the various application of transition metal halide compounds in the area of material science as non-linear optical materials, liquid crystals, luminescent materials, etc. So besides their application in material science, they are frequently used in the organic as well as organometallic transformation reactions. As you can see here, the use of metal halides in cluster growth reaction. One molecule of metal halide is able to hold 2, 3, and even 4 metal centers together. And this is how it is used in the cluster growth reactions. Cluster compounds are quite useful in the homogeneous catalysis, as they provide larger surface area for the organic substrate to interact. This slide shows the versatile reactivity pattern of metal halides. So metal, which is the carbon center, which is directly connected to the metal, alpha carbon atom, is comparatively electron deficient as compared to beta carbon center. So a wide range of nucleophiles and electrophiles are known to attack on alpha and beta carbon atoms of metal halide, and that lead to the formation of various class of organometallic compounds, metal vinylidene, metal vinyl, metal carbene, alkyls. These molecules, vinylidene, vinyl, carbene, they are widely studied in homogeneous catalysis. So as I said that the other type of classification can be made basis of positive in nature. They form ionic type of organometallic compounds. P-block metals, which have less electronegatividity difference with the carbon, they are known to form covalent type of organometallic compounds. Electron deficient metals like boron, aluminum, beryllium, magnesium, they are known to form electron deficient organometallic compound. And with partially filled d orbitals, transition metals are known to form sigma and pi bonded organometallic compounds. So this is how classification of various organometallic compounds have been made. So in organometallic compounds, some coordination sites are occupied by hydrocarbyl ligands, but other coordination sites can be occupied by inorganic ligands, such as halides, chloride, bromide, iodide, hydroxide, amines, ammonia, water, phosphines, etc. So it's important to know about the inorganic ligands, their formal oxidation state, their ability to contribute electrons towards the metal center. This is helpful in carrying out the electron counting, which is used to decide the stability and instability of organometallic compounds. So electron counting can be made in two different ways. In type A, one can consider the formal oxidation state of metal as well as the ligand. And in type B calculation, metal as well as the ligand can be considered as the neutral entities. So both type of calculation gives the same result. In case of this palladium complex, this palladium is there in +2 oxidation state. That is because of coordination of this methyl and acetyl groups. Phosphines are neutral ligands. So palladium 2 plus has 8 valence electron, 8 electrons in the valence shell. One phosphine moiety can contribute 2 electrons to the metal. So there are 2 phosphine moieties. So 4 electrons are coming from the this chelating phosphine. Methyl contributes 2 electrons, acetyl 2 electrons. So that gives total electron count of 16. And palladium is happy with the 16 valence electron count in its square planar geometry. You know that metal-metal linkage contributes 1 electron to each metal center. If there is a bridging ligand, as you can see it here, carbonyl, 2 carbonyls are bridged over to iron center. So bridging ligands contribute 1 electron to each metal center. So there are 2 bridging ligands, so 2 electrons are counted for each metal. So this is how that electron counting is carried out, just to see the stability and instability of organometallic compounds. I have included a couple of more examples of eta 2 ruthenium, eta 4 ruthenium complexes. Hints are given here, and these two complexes are obeying the 18 electron rule. They are electronically precise molecules. So normally this is the general trend. Normally that early transition metals like scandium, titanium, vanadium, they don't follow the 18 electron rule. Normally they forms organometallic compounds with less than 18 electrons. Middle transition elements like chromium, manganese, iron, etc. They mostly forms electronically precise organometallic compounds with 18 valence electron count. And metals like cobalt, nickel, rhodium, palladium, iridium, platinum, they are known to form 16 as well as 18 valence electron complex. And this is the reason why, because of their ability to form 16 as well as 18 valence electron complex, they have been widely exploited in the catalysis. So this electron counting is not only helpful in deciding the stability and instability of organometallic compounds, but it is also quite useful to know the charge distribution. Charge, if the overall molecule is having certain charges, then how that charge is distributed over various metal centers in a polymetallic system. Say, for example, in this case, that cationic bimetallic organometallic compounds of iron and palladium, the overall +2 charges can have 3 different possibility of distribution over iron and palladium. In case 1, both the positive charges can be considered as equally distributed over iron and palladium. In case 2, it can be considered that both the positive charges are localized at iron, and in case 3, one can consider that both the positive charges are localized at palladium. So after doing the electron counting, it is very clearly seen that the case 3, where both the positive charges are localized at palladium, gives more precise electron counting. 18 valence electron count for iron and 16 valence electron count for palladium. And in that way, both the metal atoms are happy. So this electron counting, I am again telling that this electron counting is not only helpful in deciding, in predicting the stability and instability of compounds, but it is also helpful in knowing the actual charge distribution within the polymetallic system. So now I'm going to talk about the various types of organometallic reactions. These are the main reactions which are used to synthesize main group as well as transition metal organometallic compounds. I'm not going to talk about all of them, but as I'll be talking about selected one. This there is a direct reaction of organohalide with metal. So alkyl halides are known to interact with metal like magnesium to form organometallic compound of the type RMgX in dry ether. Alkali metals being more electropositive, monovalent, they interact with alkyl halides and form organometallic compounds of the type RM, metal alkyls. And these organometallic compounds of S-block elements, majority of them are a very versatile synthetic reagents used in the synthesis of various functionalized organic and as well as organometallic compounds. As you can see it here that synthesis of secondary as well as tertiary alcohols can be achieved in a very facile manner with the help of Grignard reagent. The use of aldehyde instead of ketone can lead to the formation of secondary alcohol. So it is not limited to the synthesis of alcohols, but Grignard reagent is also a very good alkylating agent. There is another type of reaction that is double replacement. So metal alkyls of less electropositive metals like silicon, boron, arsenic, phosphorus, they are less reactive, less electropositive. These metals are not able to interact with the alkyl halide directly to form metal alkyls, but their metal alkyls can be synthesized by using this double replacement reaction. So what you need to do, this you have to take metal alkyls where metals are more electropositive, more reactive, and metal halide with the less reactive metal like silicon, boron, arsenic, phosphorus. Then you can have double replacement reaction leading to the formation of metal alkyls of less reactive metal. As example, one example is given here. You can have a look into this. Then next reaction type, that is oxidative addition and reductive elimination. So by definition, any reaction which is accompanied with the increase in a formal oxidation state of the metal followed by increase in the coordination number, that is classified as oxidative addition reaction. So in general, the transition metal complex which is undergoing oxidative addition possesses two types of characteristics, Lewis acidic as well as Lewis basic property, and that is because of presence of filled d orbitals as well as empty d orbitals with them. So the Lewis acidic and Lewis basic character of transition metal precursors makes them useful to be used in a oxidative addition type of reaction. You can see it here that oxidative addition of XY to this metal precursor leads to the increase in coordination number of metal by 2 unit as well as oxidation state of the metal from N to N plus 2. So this is going to be oxidative addition type of reaction. So this reaction type is basically used in the synthesis of new organometallic compounds of transition metals. These are the metals known to undergo a fissile oxidative addition, and the substrates studied in the literature are alkyl, aryl, phenyl, benzyl halides, right? And there are unsaturated hydrocarbons like alkenes and alkynes who are known to undergo oxidative addition reaction. So what makes a precursor to undergo oxidative addition? One can realize that a metal center which has energetically accessible oxidation state, I mean who can be oxidized further, can undergo oxidative addition, and metal center must be coordinatively unsaturated so that it can extend its coordination number further. So these are the two prerequisites with the transition metal precursor undergoing oxidative addition type of reaction. Reductive elimination is just opposite to that of oxidative addition. So any reaction where there is a decrease in the coordination number followed by decrease in the formal oxidation state of metal, that is considered as reductive elimination. As you can see it here, that reductive elimination of this ethyl group as a ethane leads to the decrease in coordination number of rhodium from 6 to 4, as well as decrease in the formal oxidation state of rhodium from +3 to +1. So this reaction type is considered as reductive elimination. So I would like to tell that oxidative addition and reductive eliminations are very frequently seen during the catalytic reaction. As you can see it here, I have taken this example just to highlight this point that these two reaction types are very frequently seen during the catalytic reaction. A hydrogenation with Wilkinson catalyst, as you can see it here, that rhodium 1, that oxidative addition of hydrogen gives us a coordinatively saturated octahedral rhodium complex, which upon ligand dissociation gives us coordinatively unsaturated rhodium complex. To enable this complex to add one molecule of olefin to form metal alkene complex, and then after hydrogen migration, again it forms coordinatively unsaturated rhodium alkyl complex. Then addition of a phosphine ligand to form coordinatively saturated rhodium complex, and to enable this complex to undergo reductive elimination to form alkane, to convert this alkene into alkane. This is how that catalytic cycle of hydrogenation of alkenes is there. So you know that hydrogenation of olefins is still a big challenge. I mean, a majority of petroleum products are unsaturated hydrocarbons, alkenes, alkynes, and they are of less use. And to convert them into saturated hydrocarbons, alkanes, the catalyst used are that involves expensive metals like rhodium, platinum, iridium. So if someone can replace these expensive metals with transition metals like iron, cobalt, nickel, then certainly he is going to receive lots of recognition and appreciation. So other reaction type which is quite useful in the synthesis of main group organometallic compound is insertion reaction. So as the name suggests, insertion of any group, any element of group between metal and either hydrogen or carbon. If the insertion is taking place between metal and hydrogen, then it is called as hydrometallation. Hydrometallation means insertion is taking place between hydrogen and metal. If the metal is boron, silicon, aluminum, and tin, then the reaction type is classified as hydroboration, means insertion is taking place between hydrogen and boron bond. Hydrosilylation, hydroelimination, insertion of any group between tin and hydrogen is known as hydrogenation, like that. And if G is carbon instead of hydrogen, then the reaction is named as carbmetallation or organometallation, means insertion of any group is taking place between metal and carbon. So this group can be unsaturated hydrocarbon like olefin and alkenes and alkynes, right? So insertion of a molecule of olefin across metal carbon or metal hydrogen bond certainly going to lead to the formation of a new organometallic compound of main group metal, boron, tin, aluminum, and right. So this it's not only hydroborated product. All the products of these reactions are very important from commercial point of view. So I have included some examples of hydroboration just to show the importance of the reaction and their products. So as you can see it here that insertion of one molecule of olefin, say for example ethene across boron hydrogen bond, can lead to the formation of this mono hydroborated product, right? This dialkyl boron, trialkyl boron, like that. So there are 3 boron hydrogen bond. So at the most 3 molecules of olefin can be inserted across 3 boron hydrogen bond to get trialkyl borates. And these boron hydroborated products are quite important from commercial point of view. As you can see it here that they are they play as a synthetic reagent to obtain various organic compounds. Their hydrolysis can lead to the formation of alkanes, alcohols, aldehyde, ketone, as well as carboxylic acids. So a wide range of organic compounds can be synthesized in a very facile manner by using these hydroborated products. Now another reaction type. This is also important from commercial point of view because this metal acetyl group after demetallation leads to the formation of functionalized organic acids. So how does this CO insertion or migratory insertion takes place? So basically this alkyl group, metal alkyls undergo migration. It attacks on the carbonyl carbon center and forms metal acetyl bond. And the vacant site created after the migration of alkyl group, that is occupied by incoming ligand. That incoming ligand may be carbonyl or any other ligands, phosphine, amines, any other inorganic ligands can occupy this vacant site. And it is found that the migratory aptitude of various alkyl group in this CO insertion reactions follows this trend. So bulkier group like isopropyl has more migratory aptitude as compared to ethyl and then methyl, right? So this is another commercially important reaction which leads to the formation of various functionalized organic acids through this CO insertion reaction, right? So I have included some examples, some questions which were asked during competitive national level competitive exams like CSIR, NET and GATE. Just to highlight the importance of the area. Say for example, some questions based on electron counting you can find almost in all exams every year. There are some questions asked in one or other way. So this is one I took from the paper, where you have to identify the species which follow 18 electron rule. So hints are given here. Looking at the hint, you can easily identify that this copper complex labeled as A and vanadium complex labeled as D, they obey the 18 valence electron rule, and magnesium and chromium complexes that gives 16 valence electron and 17 valence electron, and in that way they don't follow the 18 electron rule. Another example, another question from the NET exam. For the following reaction, what are the correct statement? So out of these 4 statements, we have to see which statement or what are the statements which are correct. So as I said you that it's important to have an idea about the nature of inorganic organic ligands, their formal oxidation states. That helps us to know about the nature formal oxidation state of the metal, etc. So phosphines are neutral ligands. Chloride holds one minus charge. So in that way, iridium is in +1 oxidation state. And in this reaction, what is happening basically, there is oxidative addition of one of the CS bond of phenyl group attached with the triphenyl phosphine. So there are 3 triphenyl phosphine. So one of the phenyl of triphenyl phosphine is undergoing oxidative addition to the iridium to form this hydride complex. So in statement 1, oxidation state of iridium increases from +1 to +3. Yes, it is correct because here iridium is in +1 oxidation state because of this chloride, and here iridium is in +3 oxidation state because of this hydride chloride and this carbon ion. So statement A is correct. In statement B, is it beta hydride elimination reaction? No, it is not beta hydride elimination. It is a kind of oxidative addition. Option 1 and 2 both are okay. First and second both the complex are diamantic. So answer is S, because iridium 1 with D8 configuration in its square planar geometry is going to be diamantic, and iridium 3 with its D6 configuration in octahedral geometry is going to be diamantic. So option C is correct. And in option D, it is migratory insertion reaction. So no, it is not migratory insertion reaction. This is also incorrect. So in that way, you can say that the statements given under A and C, they are correct and others are incorrect. Well, I kept this question just to tell one more thing about transition metal organometallic compounds. So transition metal instability of transition metal organometallic compounds are mainly caused by the presence of beta hydrogen atom. So wherever there is a beta hydrogen atom connected with the metal alkyls of transition metals, they have a high tendency to undergo beta elimination, or you can say olefin elimination, as it is that complete reaction is given here, how that olefin elimination takes place. So for this reaction, the presence of beta hydrogen of transition metal alkyl compounds that is required. So keeping that in mind, you can easily see that in which complex there is a beta hydrogen. So looking at this first complex, there is no beta hydrogen. The beta carbon connects to methyl group. In option B, here you have beta hydrogen, alpha and beta hydrogen, but because of this chelation effect of the complex given under B, it retains some stability. So as long as most unstable is concerned, let us have a look into the other option. The compound given under C, it contains beta hydrogen and it is N-butyl group. So as compared to compound given under B, this C should be most unstable. It will go very facile olefin elimination to form this hydride complex and olefins. This is a slide group. It contains beta hydrogen atom, but this is stable because of the stellite linkage. So I have included some questions here just to say that the topic is so hard, and in almost all competitive exams you can find several questions out of these topics. So in general, that these are the factors which governs structure and reactivity of organometallic compounds, the nature of metal carbon and metal halide bonds. It's not metal halide, that metal inorganic ligand bonding, that may be amine, water, cyano group, etc. So nature of bond, that is the one factor which affects the structure and reactivity of organometallic compounds. And then electronegativity of metal, that means polarity of metal carbon bond. And then number of d electrons, coordination number of the metal, as well as steric hindrance. So these are the common factors which are responsible for the structure and reactivity of organometallic compounds. So when you talk about the trends in the periodic table, main group metals, while going from left to right, they are left to, yes, they are more electropositive, and while going from top to bottom, because of that inert pair effect, the higher oxidation states are less stable. Mostly for it is seen for the p block metals that lower oxidation states for the heavier p block metals are more stable. About these transition metals, middle transition metals have the strong preference to form 18 valence electron complex, as I have already illustrated. And then second and third row of transition metals, they have a strong preference for paired electrons to form low spin, to form complexes in low spin states. So these are the general overview about the general observation about the organometallic compounds. How to work with such compounds. As I said you that organometallic compounds containing metal carbon bonds, a wide range of electrophiles and nucleophiles can attack on the metal and carbon connected with each other. So they are highly reactive towards moisture and air and other things present in the atmosphere. So it is highly required to carry out the reaction and manipulation under inert atmosphere, in the atmosphere of nitrogen or argon, and that can be maintained with the help of glow box or Sling line technique. And these are the common characterization techniques used to characterize the newly synthesized organometallic compounds, which includes X-ray, NMR, IR, GC, LC, etc. And these are the recommended books which one can follow to have more information about the organometallic chemistry, right? So just I am completing the part 1 of my presentation, and maybe we can have a break of 1 minute, and then I'll be starting the part 2 of my presentation. So we can have a break of 1 minute here, and then I'll come back to you. So now coming to the second part of my presentation, recent developments in bioorganometallic chemistry. We and many other research groups are actively involved in the development of sulfur-rich organometallic compounds for their potential applications in the medicinal chemistry. The sulfur atoms present in the molecular framework, they are known to act as a chemoprotectant, and they enables the drug molecule to reach to their target without untimely exchange with the biomolecules. So sulfur containing ligands are considered as one of the important pharmacophore in the biological system. So for sulfur-rich ligands, we have selected dithylcarbamate and xanthate ligands to work with. Why we have selected these ligand system to work with? There are so many reasons. The very first one is to scope for structural modification. One can do lots of modification changes with the R groups attached with the precursor molecules, amines and alcohols, which can be converted into corresponding sulfur-rich ligands. So due to ready availability of starting materials, one can design and synthesize a huge number of amines and alcohol precursors, and that can undergo nucleophilic addition to the carbon atom of carbon disulfide to form corresponding 1,1-dithiol ligands. And these ligands, why they are so special, the sulfur atom is known to bind with almost all metal centers. They are known to stabilize the metal centers in their low as well as higher oxidation states. And besides, these 1,1-dithiol ligands, they show flexible mode of binding towards the metal center. So these are the features which have motivated us to work with these ligand systems. So a very facile, a single part reaction involving amine and alcohol precursors with carbon disulfide can lead to the formation of corresponding 1,1-dithiol ligands, which on interaction with various transition as well as non-transition metal ions are metallic fragments that can lead to the formation of wide variety of complexes, mononuclear bis dithylcarbonate complexes, linear type of structures, metallo-macrocycles. They can be derived with a suitable choice of ligand in the metal ion. In the absence of these blocking ligands, one can derive coordination polymers with such ligand systems, 1,1-dithiol ligand systems. So it's all depend upon the choice of ligand and the metal center. Reports suggest the formation of metallo-bicyclic type of compounds as well as mononuclear bis DTC compounds with suitable organic ligand precursors. So all these molecules are reported in the literature already. So while going through the literature, we realize that such metallo-macrocyclic compounds are widely studied in the supramolecular chemistry, and they are well known for their host-guest binding study with a number of guest species like cationic, anionic, neutral guest species, and in the ion pair recognition. If the size of guest is suitable enough to fit inside the cavity, then these metallo-macrocycles are known to form 1:1 inclusion complex. Otherwise, they can form 2:1 host-guest exclusion complex. So, but we could not find sufficient enough work on the medicinal perspective of such metallo-macrocyclic compounds. Although organic macrocycles like calixarines and cyclodextrin, they have been widely studied in the medicinal chemistry. However, these metallo-macrocycles are scarcely been investigated in the medicinal chemistry. So we thought of to develop the synthesis of some metallo-macrocyclic compounds containing various groups in the linker framework, diphenyl ether, SO2, amidic, dithacarbamate, arginotine, etc. And it was anticipated that incorporation of various biologically relevant groups would certainly enhance the biological profile of these metallo-macrocyclic compounds. And all the molecules have been thoroughly characterized by various crystallographic and various spectroscopic as well as crystallographic techniques before going to screen them for their potential anti-cancer activity. So, for example, we have optimized the synthesis of these diamides and used them into the formation of corresponding 1,1 dithiocarbamate ligands, which on interaction with arginotine diphenyltine gives us these metallo-macrocyclic compounds in good yields. All the molecules are well characterized, and that tin NMR spectrum clearly suggests the phase purity and the presence of hexa-coordinate tin centers in these molecules. That range of tin NMR signal confirms the presence of hexa-coordinate tin centers in these molecules. All the molecules are optimized by DFT level calculations, and the structural parameters obtained theoretically were compared well with the similar parameters obtained experimentally. And then we screen all the molecules for their potential anti-cancer activity against heptonoma and neuroblastoma cell lines, HEP3B and IMR32. And we observed very interesting anti-cancer property particularly for metallo-macrocyclic compounds holding diphenyltine centers. As you can see it here, even that ligand precursors, diamino ligand precursors, they have also shown good anti-cancer activity, but the activity of these ligand precursors is further augmented upon the formation of their corresponding metallo-macrocyclic diarginotine compounds. In some cases, say for example 4, which holds 2 furfuryl group at the nitrogen atom of dithacarbamate, that shows more than 25-fold better activity as compared to the well-known metallo drug cisplatin. So these activities are considered to be because of the presence of various pharmacophores present in the molecular framework, that diphenyl ether, amidic, dithacarbamate, as well as diarginotine, which are very crucial for their enhanced anti-cancer activity. So apart from that, we have realized the importance of ferrosinyl group. Reports suggest that the biological activity of ferrosinyl containing compounds are associated with the attachment of ferrosinyl group to either biologically relevant molecules or with the molecules that do not exhibit biological activity. Right? So these are the characteristic features of ferrocene, which makes them more demanding to be utilized for the development of argumentally compounds of biological relevance. So ferrosinyl group is reportedly involved in the generation of reactive oxygen species. It is responsible for the improved selectivity and activity. It helps to overcome the resistance barrier, increases the lipophilicity, it provides redox active sites, and it is known to enable the easier passage of drug molecule through cell membrane. So these are the characteristic feature of ferrocene group, which makes ferrosinyl group so crucial, so important to be incorporated with the other biologically relevant groups or other molecules to enhance the better biological profile. As you can see here that tamoxifen is a well-known drug, and the anti-cancer activity of tamoxifen against breast cancer cell line MCF7 is more than 10 macromolar IC50, that is 50% inhibitory concentration. But after the incorporation of ferrocin group into the structure of tamoxifen, that gave us ferrocifen, the activity of this ferrocifen against the same cell line is found to be almost 10 times better than the tamoxifen, right? So you can just see that how the biological profile of a well-known drug can be further increased simply by incorporating the ferrocinyl group into the structure of that drug. Similar observation has been made with the chloroquine after the incorporation of ferrocinyl group into the chloroquine structure, that give us ferroquine, and with improved biological activity. So keeping that in mind, our ongoing strategy is to incorporate ferrocinyl group, to attach ferrocinyl group with other biologically relevant groups like amides, dithiocarbamate, biologically relevant transition metals, and to see the synergetic effect of this ferrocene containing hybrid materials on the overall anti-cancer property of the molecules. So for that, keeping that in mind, we have developed the synthesis of various amine precursors, secondary amine precursors, suitable for the development of corresponding dithiocarbamate and their complexes, along with the tertiary amines. All the molecules have been characterized well with the various spectroscopic as well as crystallographic study. That appearance of UV visible band around 450 nanometer corresponds to the ferrocinyl group because of that charge transfer. And then these molecules have shown the ability to form a number of intermolecular as well as intramolecular hydrogen bonding interactions as revealed by their single crystal X-ray diffraction study. All the ligand precursors, secondary amines as well as tertiary amines, they have been screened for their potential anti-cancer activity against a wide range of cell lines, breast cell lines, neuroblastoma cell line, liver cell line, HepG2, and the data is summarized in this table. As you can see that in general, the activity of tertiary amines are found to be superior than the secondary amines. That may be probably due to the increased number of biologically relevant groups, amide groups with the tertiary amines, and in particular, the anti-cancer activity of compound 4B and 5B that holds. These are basically tertiary amines that holds para-methylbenzyl and para-methoxybenzyl at the amidic nitrogen. That gives us optimum activity against all the cell lines, almost. And they project that study project that these molecules can be a potential candidate for the discovery of anti-cancer drug. The presence of this secondary amine moiety in these molecules can be utilized for the further derivatization into more biologically relevant molecules, showing pronounced better activity than what we have reporting here. Okay, so some of right. So after that, what we thought of, let us see the influence of chirality on the biological activity, anti-cancer activity of these amines, particularly the tertiary amines showing good activity here. So we have incorporated that chirality at the benzylic carbon center, and we have seen that one of the enantiomer with S type of chirality that gives us M type of helix. R enantiomer gives us P type of helix, and we have seen a huge difference in their anti-cancer activity against all the cell lines, almost all the cell lines. As you can see here, that this black bar that denotes the S enantiomer, a red bar denotes the R enantiomer. So activity of R enantiomer is found to be much better than the S enantiomer against all the cell lines. So we have reported the influence of chirality as well as redox potential on the cytotoxic anti-cancer activity of these enantiomers. So in order to further derivatize the secondary amines into their corresponding dithiochromate and metal complexes, some new chiral secondary amines have been synthesized and characterized by various spectral study. And then some of these amines, secondary amines, have been taken after characterization. These were taken for the further derivatization into corresponding dithiochromate ligands. As you can see it here, that in situ formation of dithiochromate from chiral secondary amines containing ferrosinyl group into the linker, and then this DTC upon interaction with various metal centers like copper, nickel, zinc, that has led to the formation of various transition metal with dithiochromate complexes holding chirality at this R groups. All the molecules have been characterized well with various spectroscopic as well as crystallographic study. Single crystal structures of some of the representative compounds have been determined with the help of a single crystal X-ray diffraction study. The appearance of a very downfield signal around 206 in the 13C NMR spectrum of these compounds confirms the presence of coordinated dithiochromate ligands in these compounds. And then in order to increase the number of pharmacophores into a single molecular platform, we have made use of trivalent cations like ruthenium 3+, cobalt 3+, iron 3+, and we have successfully derived a number of tris dithiochromate complexes holding various ferrosinyl amidic amino groups in the molecular framework as well as chirality, and it is anticipated that with the increased number of biologically relevant groups, these molecules will give us even better anti-cancer activity than what we have observed before. So with this, let me conclude my session by saying that the presence of arginine, dithiochromate, and amidic groups into a single molecular platform evidently enhance the anti-cancer property of molecules. Further cumulative effect of ferrocene, amine, and amino groups of various ferrocene functionalized secondary and tertiary amines increases the biological relevance of the molecules. Influence of chirality and redox potentials on anti-cancer property of several ferrocene functionalized secondary and tertiary amines have been demonstrated. The future aspect is to functionalize amino handles of amide functionalized secondary amino methylferrocene into a diverse bioactive ligands with the incorporation of several biologically relevant groups into the metal dithiocarbonate framework. We are expecting better cytotoxic data with some optimum molecules showing activity in nanomolar concentration. With this, I would like to close my session. Again, I would like to acknowledge UGC HRDC Gujarat University for giving me this opportunity to interact with you. Program coordinator Professor Dilip Basawa sir, and then of course my former and present PhD students who have contributed and did all this job with lots of sincerity, hard work, and dedication that has led to the outcomes what I have presented here. Thank you. Thank you.
Thank you very much, sir. It was very nice and informative session for all. Thank you very much once again.